In this video, we'll consider three important Unit 1 test questions. I am Anil Kumar. Welcome to my YouTube channel. We have many videos for you and playlist where these videos are organized for better practice. Here, we are going to consider a very important question from test point of view. We're looking at discontinuous functions and limits. The question here is, find the integer values of m and n if the limit x approaching 3 for x square minus x plus m over x square minus n is L, where L belongs to real numbers. So the limit exists for this particular function. We need to find what could be the value of n and m. Now, there are a couple of ways in which it can be answered. Now, first condition is that for the limit to exist, the denominator should not be 0, right? If the denominator is not 0, you divide by something which is a real number, you can get a limit of the function, right? So one value could be that n, or rather, let's consider a case where the denominator is not equal to 0. That means x squared minus n is not equal to 0. For x equals to 3. Now, if I substitute 3 here, what do I get? I get 3 squared minus n is not equal to 0. That means n is not equal to 3 squared. So that means n is not equal to 9. So if n is not 9, but it could be n belongs to any other integer value, right? N could be anything else, but not 9. In that case, we find that the denominator will not be 0. So the limit will, of course, exist. So in this case, n is not equal to 9, but m has got no restrictions. M belongs to the set of integers because we are given that we need to find the integer values of m and n, right? So that I will say is our case 1, right? Okay. Now let us take case 2. So case 2 is when n square minus n is equal to 0 for n equals to 3, for x equals to 3, right? Now it means that 3 square minus n is equal to 0, n equals to 3 square, or 9. So if n equals to 9, then what is the value for m? So that becomes the part 2 of this particular problem. You understand? But remember, part 1 is very essential to understand, and that is n could be any other number except 9. In that case, the solution is this, right? But if n is 9, in that case, m is restricted. Perfect. So let's move on to the next page and look for case 2, right? So now let me write down here case 2, where we know that n is equal to 9. So in that case, let me rewrite the limit given to us as x approaches 3 for x squared minus x plus m, and we'll substitute 9 for n. Correct. Now, as soon as you do that, you understand that the denominator can be factored, right? And so, a couple of ways to do it. We could write this as x square minus x plus m. And here we have x plus 3 times x minus 3. Now, for the limit to exist, we have this factor x minus 3. We should have x minus 3 a factor in numerator also, right? So that means we are expecting a whole, right, at x equals to 3. In that case, limit will exist, right? Then L belongs to real numbers. Is it okay? Otherwise, the limit will not exist. So since we want a whole at x equals to 3, we are looking for a common factor. So we know that the numerator x square minus x plus m should be equal to 0 for x equals to 3, right? So let's substitute the value and check, right? So we get 3 square minus 3 plus m equals to 0. So 3 square is 9 minus 3 plus m equals to 0, right? Now that gives you m equals to minus 6, right? So if n is equal to 9, then m is minus 6, correct? So we get our solution n equals to minus 6 for n equals to 9. That becomes another solution. Well, you can always check this solution because if I put minus 6 here, then we have x squared minus x minus 6 over x plus 3 times x minus 3, right? The numerator can be factored, right? So we have what? 3 times 2. So we get x minus 3 times x plus 2, right? Over x plus 3 times x minus 3. So they cancel. And we're looking for x plus 2 over x plus 3. Now, in this case, we have to find only the value of m and n, right? If the limit exists. But you can also find the limit, right? So you can find the limit by substituting x equals to 3 in this particular case. So in this case, you'll find that limit L will be equals to 3 plus 2 over 3 plus 3, which is 5 over 6. In this particular example, we don't have to calculate it. However, it could be one of the question, a part of the question at least. But I hope with this you have understood the strategy of solving similar questions. As you can see, a rational function. It is discontinuous at x equals to 3 if n is 9. So in that case, we should have a factor x minus 3 in the numerator so that we have a whole. And once you have a whole, then the limit can exist, right? So that is the concept behind it. I hope it is absolutely clear. Now let us understand if the function could be continuous but not differentiable. A very important communication based question for you. Provide examples of the functions that are continuous but not differentiable in their domain. It is extremely important and it helps you to understand the basic concepts. Now, two things. One, the function is continuous. That means at every point, actually, you can find the derivative. But says not differentiable in the domain means there are a few points within the domain of the function where it is not differentiable. So the function will not be differential and continuous. Those could be three conditions, right? So there are three conditions when this can occur. One is when you have a cusp or you have a corner or you have a vertical asymptote. So these are the three conditions when a function could be continuous but not differentiable. So if I sketch the graph of each one of them, it will be absolutely clear to you. So let me do that. So I'll just sketch three functions here. Cusp. Cusp is a graph which is kind of like this. Do you understand? So as you can see, it is a continuous function. However, at the origin O, if you want to find the derivative of this function, it is infinitely large. It is not a real number. So, for example, the function could be y equals to x to the power of, let's say, 2 over 3. Now, this particular function, if you find the derivative of this function, it will be what? 2 over 3 times x to the power of 2 over 3 minus 1, right? Which will give you minus 1 over 3. So, as you can see, that at x equals to 0, you can see that y prime or the derivative is infinitely large. And so clearly, it is not differentiable at origin, right? Now, let's take up another example, which is based on corner. A common function is absolute value of x. So if you have y equals to absolute value of x, you know it is continuous. However, it is not differentiable at 0. So because at 0, you can see you can have many tangent lines, right? All these lines could be tangent at 0. We are not very sure which one is the correct one, right? If you see, the derivative from the left side is negative 1 and from the right side is positive 1. It is not the same. So that is also is not differentiable. Perfect. So if you see y equals to absolute value of x, it is a continuous function, but y prime at x equals to 0 does not exist. Make sense? The third function is where you have a vertical asymptote. The graph of the function could be something like this. You see that vertical asymptote at the origin? Now, in all the three examples, I have taken functions, basic functions, which where we are considering differentiability at the origin itself. While these could be translated left or right, and so you could have any other point also. Perfect. So this is a function which looks like y equals to cube root of x, right? Let me write y equals to cube root of x. Now, if you find the derivative, which is y prime, will be 1/3 of x to the power of 1 over 3 minus 1, which is minus 2 over 3. So clearly, here what you notice is that at x equals to 0, y prime does not exist. So that becomes our third example. However, as you can see, the three conditions where the functions are continuous but not differentiable are when you have a cusp, or when you have a corner, or we have a situation with a vertical asymptote, as given in the last example. I hope it makes sense. Here is the last question from IB test paper. We'll try to find the equation of the tangent line from the given conditions. Check our playlist for many more related examples. The equation of the line that passes through the point 0a and is tangent to the function f of x equals to 1 over x is y equals to mx plus a. Find the slope of the tangent line in terms of a. Extremely good question which has been seen in past test papers. I hope its solution will help you. Well, in case you want to learn directly from me, feel free to send an email on globalmathinstitute@gmail.com. Our students are right there on the top, getting admission to the best universities, even with scholarships. Now, let's try to understand the approach for solving such a problem. We are given a point which is 0a. So a is the y-intercept of this function, and therefore, in the equation of tangent line, we have mx plus a, right? And this is also tangent to a function f of x 1 over x. So let's begin from that place that we have a function f of x which is equals to 1 over x. We need to find what m is. That means the gradient, the slope. So let's find the gradient, that is the derivative of this function. So f prime x will be minus 1 over x squared. Some of you prefer to write this as x to the power of minus 1 and then use the power rule, which is minus 1 x to the power of minus 2, which effectively is minus 1 over x squared. Perfect. Now, the key idea here is that we do not know the point on the curve, right? So, what could be that point? This is what we are looking for. So, we'll assume that let point on the curve, you can say f of x, be what? So, we have to give some value. So, let's say if that value is, let's say, c, right? X value, then the y value will be 1 over c, right? Because the function is 1 over x, right? So think like this: if x equals to c, then f of c is going to be 1 over c. Therefore, the coordinate point will be c 1 over c. You get the whole idea, right? Great. So let's continue from here. We know the slope. So let's find the slope of the function at the point c, right? So of course, the slope of the function at the point c is going to be minus 1 over c square. Now that is the slope, and we know that the y-intercept, let's call this point as a, y-intercept is 0, a. So a tangent line is going through the point x equals to c and y-intercept 0, a. And therefore, we can write that the equation of tangent will be what? We know the slope, right? So we can write the equation of tangent is y equals to minus 1 over c square, which is the slope, x plus a, since a is the y-intercept. Now, we have too many variables here. How do we get the value of c? That is kind of critical. Since we know that the point is actually c1 over c, which is also on the curve function, reciprocal function. Now the idea is, how do we get the value of c in terms of a? So for that, we know that the coordinate point, which is common to the tangent and also to the curve, is basically c1 over c, right? Substituting this point in the equation, we can actually find c in terms of a. So let's rewrite this. What we get is y value of 1 over c, right, equals to minus 1 over c square and x value of c, right, plus a. So that is what we get our equation as. Now simplifying, we can easily write down that in this particular case, this is minus 1 over c, cancelling one of the c's. We have 1 over c equals to minus 1 over c plus a. Bringing them together, we get 1 over c plus 1 over c equals to a, or 2 over c equals to a. Correct? Or you can say 1 over c equals to a over 2, right? Is that clear? So we get the value of 1 over c as a over 2. And if I want to square it, in that case, what happens? So 1 over c square, squaring both sides, will be a square by 4. You get the whole idea, right? So 1 over c square is a square by 4. So 1 over c square is a square by 4. Substituting this back to the equation, we get our equation of the tangent line, right? So I'll just write it on a fresh page now, right? So, so what we had earlier was that we had the equation that y equals to minus 1 over c square x plus a, and we just found that 1 over c square is basically equal to a square over 4, right? Substituting this in our earlier equation, we can write down y equals to minus a square over 4x plus a as the equation of tangent line required in this particular case. You get the whole idea, right? So a could be any value, and we can get this kind of an equation. So from here, if you compare it with the line y equals to mx plus a, the slope is what, right? So we get the slope m as equal to minus a square over 4. Makes sense? Correct? So that is how you can get your equation and relate it to the slope. So if you sketch a graph of this, what basically we are saying is that the curve 1 over x on this side will be kind of like this, and this particular line, which is the tangent to this, for example, correct? So that point which we have considered is c1 over c. You see that? And this point is at a, and that's the tangent line which we are talking about, right? So I hope the situation is absolutely clear. It's a very wonderful question. Feel free to write your comments and suggestions. In case you like and subscribe to my playlist, that will be great. Thanks for your valuable time and all the best.